Up to this point, our concept of limits have been as follows. As we approach x, what does y equal? And when we talked about approaching x, we talked about approaching x from the left side and the right side, and as long as we were getting close to the same y value, we said that function had a limit. Today we're going to shift the discussion to what we call one-sided limits. One-sided limits are exactly what they sound like. We're going to take and approach x from only one side, either the left or the right, and state what y is getting close to, and that would be the one-sided limit of the function. So here I have a piecewise function. It's graphed down below, and we're going to find the limit of f of x as x approaches 1 from the positive side, so that means moving in this way. When I find the limit of f of x as x goes to 1 from the negative side, that means I'm approaching 1 from this side. So you'll see that in this case, at 1 from the positive side, we get closer and closer to an x value of 1, and our y value gets closer and closer to a y value of 2. Now, as we approach 1 from the negative side, again, we're getting closer and closer to an x value of 1, and our y value is getting closer and closer to a y value of 1. So you'll see in this case that as we approach from the left, we get a limit of 2, and as we approach from the right, we get a limit of 1. In our initial understanding of limits, this function wouldn't have a limit as we approach 1. But because we're allowed to approach from either side and do a one-sided limit, we have values for the limit of this function now. Let's do another one. So I want to find all of these one-sided limits. As we approach -3 from the positive side, that means we're going in this direction. Our y value is getting closer and closer to, it looks like, roughly 0.5. As we approach 3 from the negative side, or -3 from the negative side, it appears that we're getting closer and closer to, I don't know, -0.8. And now we'll look at, as I approach 2 from the negative side, means I'm over here and approaching 2, and it appears that my y value is getting closer and closer to -0.5. As I approach 2 from the positive side, my y value is getting closer and closer again to 0.5. So you'll notice in this case, as I approach from the left and as I approach to the right, I end up with the same limit value. There's a theorem that kind of goes along with this. Suppose that you take the limit as x approaches a constant from the negative side, and it gets you some value L. And the limit is x as we approach that same constant from the right side is equal to some value R. Then the limit as x approaches that constant value, notice there's no left or right side on this, so this is like the initial limit notation that we first discussed. That limit's going to exist if and only if the right-sided and left-sided limits values are the same. So in this same problem, if we look at, once again, x approaching 2 from the negative side, we got -0.5. X approaching 2 from the positive side, we got -0.5. We can now state that the limit as x approaches 2 is also -0.5. So this actually has a limit value at 2. And we also know f of 2 is completely different. That equals -1. Now let's talk mathematical definition for a continuous function. The non-mathematical version was no breaks, poles, asymptotes. So a continuous function is one that's defined at a value c, and c is in the domain, and f of c equals some number. So that means it's defined basically. There's a limit as x approaches from the left of some f of c value, and a limit as x approaches c from the right approaches that same y value. So in other words, the limit of f of x as x approaches c is basically equal to f of c. We get a straight substitution limit, which is what we've been doing all along. Let's take a look at these values. We have the limit as x approaches -7 from the positive side. -7 is over here. On the positive side, it appears that my value once again is 1, 2, 3, 4, -4. And as I approach -7 from the negative side, I get that same value. So since my limit from the left and the right are the same, I can say that the limit as I approach -7 is that value of -4. If I approach 5 from the positive side, moving this direction, it appears that I'm moving to -infinity because I'm not approaching anything. It just keeps going down. As I approach 5 from the negative side, which is here, it appears that my y value is getting closer and closer to 4. Since the limit from the left does not equal the limit from the right, we say this function has no limit, even though it has one-sided limits. So now we're going to use this graph to determine the limit and discuss the continuity of the function. As I find the limit as x approaches -2 from the positive side, that appears to be going to positive infinity. As I go to -2 from the negative side, that appears to be going to -infinity. Thus, we say that the limit as x approaches -2 does not exist. And therefore, since that limit does not exist, the function is not continuous at x equals -2. So we want to know if the functions below are continuous at the value of c. I take a look at this problem and I notice I have a perfect cube in the denominator, which we know factors into x plus 1 times x squared minus x plus 1. And that's all over x squared plus 1. And I can basically tell this is not going to be continuous when x equals -1, but they want to know, is it continuous at 1? And since I can plug 1 in and I get no undefined terms, we can say yes, it's continuous. When I take a look at this function here, I have f of x is equal to x squared plus 5x plus 6 over x plus 4. And I look at the numerator and say, well, I can factor that into x plus 2 and x plus 3 over x plus 4. And I want to know, is this function continuous at x equals 4? Well, clearly, if I plug x equals 4 in to the denominator, this function goes undefined. It'll have an asymptote. And I can clearly say, no, that's not continuous. That's all we've got. Fill out your lesson summary and do your My Math Lab, and we'll discuss these more tomorrow.